The first thing to get our head around is the actual logic of an induction proof and what it is. You've seen deductive proofs. Now, deductive proofs are what you've done in, say, geometry. They're basically if-then statements. If you know this is true, then you can imply this is true. And that's a deduction. An induction is when you induce the proof rather than deduce the proof. So it ends up being a series of statements linked using what we call logical connectives. So some statement will be what we're trying to prove. So we'll just call that SN. Some statement that needs to be proved for every single case, so it's always true. We look at the first case, so we'll call that S1. Sometimes called the base case. Not always the first case is n equals 1. Sometimes it might be for even numbers, so it's n equals 2 and things like that. Then we make an assumption, because remember, we're trying to prove something. We don't know it to be true yet. We want to prove it to be true. So what we do is we make the assumption that it is actually true for the general case. Then we go and try and prove it's true for the next case. And that becomes a deductive proof. So there's actually a deductive proof inside the inductive proof, because that becomes the if-then statement. We say, well, if I know it's true for k, then I can imply it's true for k plus 1. So that's basically what you're doing in an inductive proof. So you need these things. Now this is all logic notation, which we'll go into far more detail next year. But what it basically is saying is, that symbol is and. So if you have the first case, you know the first case, and you've got this assumption, then from there you can imply k plus 1 is true. So if you've got all those conditions met, right, you know the first case is true, you've assumed that, so you've got these two things, but if from those two things you can imply, so there's your if-then statement, if you can imply then that k plus 1 is true, then from that whole thing, you can then imply it's true for every case. And that's the induction. You induce it's true for every case. So the actual structure of the proof then. So the first thing, oh, by the way, you don't have to write down step 1, step 2, step 3. I've seen people do it, but you don't need to. But the first thing you're going to try and do then is that base case. Let's prove that to be true, because that's one of the things we need in our proof. So n equals 1, or whatever the first case happens to be. The second step then is, well, we need to make that assumption, because we need these two things. Okay, so we make our assumption, and the assumption basically matches what it is you're trying to prove. If we're using set notation, then we'd say something like this. Well, we're going to assume it's true for n equals k, where k belongs to the set of positive integers. That's usually what we're trying to do, usually for positive integers. Then comes the deductive part of the proof. We're then going to prove it's true for k plus 1. When you conclude your deductive proof, and this is a bit that's often left out or often written incorrectly, but your conclusion is saying, hey, I've just proved it's true for k plus 1, but it will only be true if my assumption is true. Remember, you needed those two things. You needed the first case and you needed the assumption. So we need the assumption to be true. And so that's what we're saying. I've proved that k plus 1 is true if it is true for n equals k. I suppose the if-then statement is sort of the reverse of the if-then statement, because if you read this a different way, you're saying, well, if it's true for n equals k, then it's true for k plus 1. So if this is true, then this is true. So the last step then becomes the induction, is where we're saying, well, hey, we've got all these conditions we needed. I can now induce the proof, because I know it's true for 1. We just proved it's true for k plus 1 if it's true for k. Well, if you think about that logically, well, I've proved it's true for 1. I've proved it's true for k plus 1 if it's true for k. Well, it's true for 1, therefore it's true for 1 plus 1, 2. I now know it's true for 2, therefore it must be true for 2 plus 1, 3. And that's the inducing of all the possibilities, because you could keep doing that forever and you'll get every positive integers. That is the induction. So that's the last step there. We conclude the overall thing with the inductive part where we say, well, since it's true for 1, then it's going to be true for all positive values by induction. Those last 2 words are very important because we say, okay, we're inducing the proof by induction. Now, in set notation, I'd probably write something like this. Since the result's true for n equals 1, then it is true. Now, the upside down A means for all. So, for all n that belong to the positive integers by induction. Okay, so let's look at some. The first type we look at is a series. Now, we've got a formula for arithmetic series. We've got a formula for geometric series. But not all patterns are arithmetic or geometric. There are other patterns, such as this one, which is the sum of odd squares. And what we're saying is, well, this should be the formula for it. If we wanted to use it, that would be the formula. And that's what we're going to try and prove. Okay, so the first case. This is probably one of the only times you'll ever see me write down left-hand side and right-hand side. But for this one, I'll say, well, okay, the left-hand side of what I'm trying to prove, I'll sub in n equals 1. I'll get 1 squared, because that's the first term here. If I sub into my general term, I'll get 1 squared, and that's what? The formula tells me I should get 1/3 times 1 and put the substitution steps in. Because remember, it's a proof. You're showing them where it's all coming from. So show the substitution step. Yeah, of course it's obvious that 2 minus 1 is 1. But don't just write down 1. Show where it came from. I subbed into this formula and I got 2 minus 1. And then I got 2 plus 1 in the next one. So I get 1/3 of 1 times 3, which is 1. Ah, yes! They are the same thing for this first case. So hence, I've done the first bit that I want. I've shown that it's true for n equals 1. You wouldn't write that down, I'm just pointing out, okay, I've done S1. Okay, I've got that bit. Assume the result is true for n equals k, where k belongs to the positive integers. But write down your assumption. Again, don't be lazy. Essentially, you're writing down exactly the same thing, but instead of writing n, I'm writing k. But put it there, that's part of your proof. Prove the result is true for n equals k plus 1. Again, write down what you're trying to prove. Because someone's reading your proof. How do they know that you've proven it if you haven't told them what you're trying to prove? So you need to have that there. So that's what I'm trying to prove. So for k plus 1, the last term there would now be 2k plus 1 all squared. And on the right-hand side, it would now become 1/3 k plus 1, 2k plus 1, 2k plus 3. So again, to highlight the lazy bits people leave out. The first thing you write down is what we're trying to prove. It's amazing how often that's left off. But again, if you don't write it down in your proof, when you then say, prove the result's true for n equals 1, person reading your proof's going, prove what's true for n equals 1. How do they know you substituted incorrectly? You haven't written down what it's a proof. And again, write down what you're assuming. Write down what you're trying to prove. Let's now go and prove it. So I will start with the left-hand side, but with these series ones, what we tend to do, the first step is we break it up and go, I'm going to write down the first k terms plus the k plus 1 term. All right, so I wouldn't put this bit in, by the way, this is just highlighting what I've done. So I would write down what the sum of the first k terms is, and then add the k plus 1 term, because the sum of the k terms, if you look at it, that was our assumption. So whilst I have plus ... and what are all these things, I can now substitute something in for that I can now work with. So we sub the assumption in. 1/3 k, 2k minus 1, 2k plus 1. But again, it's a proof. How did you magically go from this line to this line? Let them know. This is what I've been talking about with when you're working on your page, just work down. You don't work across the page, you work down the page. Keep the right-hand side for explanations, because now what I'm going to say is, well, that was by my assumption. That's how I can do this substitution, because remember, I assumed these two things were the same. To explain what you're doing. Right, let's now play with it. But keep an eye on what you're trying to prove. So I'm not going to expand this whole thing out. I would end up with a whole heap of algebra and it'd be a lot of work when I know that my answer needs a factor of 2k plus 1. And I already have a common factor of 2k plus 1. So why expand out only to refactorize it back again? So I'll pull that factor out. Now I'm just playing inside the brackets. A third k, 2k minus 1, plus 2k plus 1. There is also a common factor in those two things which you might not immediately see. But if you look at what we're trying to prove, there is a factor of 1/3. These two have a common factor of 1/3. Pull the third out, and then, okay, this 2k plus 1 now becomes 3 lots of 2k plus 1. But I've pulled out the common factor of 1/3 that I need. I'm basically left now with a quadratic, which are very easy to factorise. So playing around with it, we get 2k squared plus 5k plus 3, which indeed does factorise to be k plus 1, 2k plus 3. And that is what we were trying to prove. So now I finish off the deductive part where I say, well, hence, my result is true for k plus 1. If that assumption that I substituted in is true, because that was the key part here. This proof only works if that assumption's correct. If that assumption's wrong, then this proof's a piece of garbage. So that's why we write it down. We're making the point that yes, I've proven it to be true for k plus 1, but it only works if my assumption is correct. So that's the deduction. Now we finish it off with the induction. Well, since I know it's true for 1, then it must be true for all integers by induction. We can now induce it to be true for everything. The structure of the proof is so important. That's what we're interested in when we're looking at it. Do you understand the logic behind what you're doing? Do you understand the structure of an induction proof? The actual proofs themselves, I mean, you look at that was not a difficult thing to do. It's a little bit of factorising, but you can get it together quite easily. That's not where all the marks lie in an induction proof. It's what we want to see, you know what you're doing. Okay, let's try another one. They might put it in sum notation rather than physically write the sum out. Okay. Now, sometimes you might like to actually write it out so you get a feel for what the pattern is. And notice when I wrote it out, I didn't write 1 on 3, 1 on 15 and so on. I wrote the two individual terms in so I could get a feel for what it is. Okay, 1 times 3, 3 times 5, 5 times 7. Okay, I can see what's happening here. It's odd numbers, consecutive odd numbers multiplied together. Well, let's see if it works for the first case. Left-hand side will be the first term is 1 on 1 times 3, a third. And if I plug it into the formula, I get 1 on 2 plus 1, which is also a third. It works for the first case. I'm going to assume it's true for all positive integers. In other words, that is what I'm assuming. Now, I've written it out in the full series there. I could have used some notation as well. Prove it's true for n equals k plus 1. So this is what I'm trying to prove. The last term now becomes 1 on 2k plus 1, 2k plus 3. And what I'm trying to prove will be k plus 1 on 2k plus 3. Okay, let's do the proof. Well, it's a series type, so I write down the series, but now I'm going to rewrite it, highlighting I've got the assumption plus the next term. So now I can sub that in using my assumption. I've got algebraic fractions to play with. So this time, have a look at what we're trying to prove. The bottom of the fraction is 2k plus 3. So I know I'm going to have to get a denominator of 2k plus 3. Well, algebraic fractions, let's put them together. So common denominator, 2k plus 1, 2k plus 3. On the top then, I have k times 2k plus 3 plus 1. Well, the top expands out. Don't waste a lot of time trying to factorise this, because you already know what one of the factors has to logically be. If I'm trying to prove the denominator is 2k plus 3, then this 2k plus 1 must be a factor of the top. And the other factor? Well, hang on. If I'm left with k plus 1, that's got to be the other factor. Hey, they don't know I didn't actually do it. I just wrote it down. Now, if you're unsure, for sure, expand it out and make sure that, oh yeah, that is the right thing. But logically, that's what it has to be for this proof to work. So the 2k plus 1s cancel, and I get the k plus 1 on the 2k plus 3, which is what they want. Hence, the result's true for k plus 1 if it's also true for k. Well, since it's true for 1, then it's true for all by induction. So the three key parts of the induction proof. Prove it true for the first case. So this is setting it up. Assume what it is that you're being asked to prove. That is your assumption. Then state what you're going to try and prove, the k plus 1 case. Okay? Then the actual proof. The actual proof is a deductive proof. So we provide explanations for anything that's not obvious. How did you go from this line to this next line? Now, in a lot of cases, it's simply that statement, oh, by the assumption, I could do this. But it might be some other theorem you end up using, substituting in, whatever it is. If it's not immediately obvious, explain it. And then you conclude with your if-then statement. That's how you finish a deductive proof, with an if-then statement. And then you tie it all together. You induce the solution. You're basically putting these two things together and inducing the proof. All right. 2A, we'll have a go at some inductions.